Thanks. Oh, lost it. Second try. So thanks for the introduction. So actually, we are very thankful for the last question regarding actually to what extent can you represent a method in the existing taxonomies and ontologies. And what we're presenting today is what we've, together with Sciex, have done in the mass spec world and what our particular use case was. So I'm going to introduce you the concept and the idea that we have, and then there we actually did all the deep dive technical work. We'll give you some details on that and also emphasize some challenges that we had. So just relax during the next 15 minutes. So basically, we had a use case, I think, that you can find in many of analytical labs, maybe even in yours. This is basically in the pharma DMPK area. They have a LIMS and they have MS workstations. And basically, the general process is to start from the LIMS, then basically where method information is stored, usually in a text-based form, describing how to prepare the sample, how to set up the instrument, what the measurements parameters are, applying them then, walking to the workstation, measuring the samples there, and basically transferring the text-based analytical method to basically implementing that then in the analyst software of the individual workstations, transcribing it, and doing that on every individual instrument you're measuring that. And we thought that maybe we can have a better approach to that makes it more reliable on the one hand side, and having also a bit better control about the methods that are like lying around in the labs, that you don't have multiple versions, etc. So we were thinking, why couldn't we just start basically on the right-hand side by creating the method as you would usually do on the MS workstation, then storing all that information in an ADF file, and then basically transferring that to the LIMS so that the LIMS acts as a method repository and has all methods that are around in the lab in the LIMS stored in the form of an ADF file. And then if you want to measure something, you just select from the LIMS the method file, which is then sent together with basically the sample list back to the workstation as such. And basically at the end of the workflow, when you generate the data, you want to archive that. So the idea is then also so storing the actual raw data in the same ADF file, so that you have a compiled overview of the complete method with all parameters and the actual raw data in one file, and then can handle it in your archive. So how did we approach that? To give you like a more tangible example of what this actually looks like, so this is not the method from our lab, so you don't need to look for any secrets in there. So it's a published method that we took as an example that represents basically the common terms that you would find there. So starting with the red part, how you would dilute the sample, then describing the device that is used, which detector, basically which software was run in there, what column was used, and then basically the process method where we did at which wavelengths did you measure, and then what were you looking for in the MS results. And then the right-hand side, you see how we actually exemplary map that to the Allotrope Foundation ontologies, and that basically makes this human readable text block in a unique machine readable way that can be interpreted directly from, for instance, from the MS software as such, and makes it as such also there's only one way of interpretation. If two technicians would read the left-hand side, they might implement it differently in the instrument, especially because there's always something missing. I don't see anything about like integration parameters or whatever that you don't find in there, but it's obviously in the machine readable version, you know if something is missing or not. So this looks at light in reality. So this is basically the model. Actually, Ostus helped us setting up the model for that to model a mass spec experiment and all the method information in there. So you see it looks complex, but it's not just a graphical model. To give you an impression how this actually looks like, one example, so for instance, a period, which is just the one measurement as such. So it's basically consisting of a mass spectrometry run. It has a discrete methods file from the Analyst software. It has basically consistent of an HPLC that's doing the liquid separation before, and it has a sample, etc. So that's basically what is, if you blow up that model, what you find behind that. And now, Blair will tell you how we actually put that into practice and what this look like really in the real world.
Thanks, Henning. Good morning, everyone. My name is Blair James. I'm the technical lead for the Sciex Compliance Software and Professional Services Group. We've been working with Bear for about a year now on this project. We ran into a number of technical challenges that I think would be common to many implementations of this sort. The Analyst software is in the maintenance phase of its life cycle. So we might call it legacy software. It's quite monolithic and was not designed with the intent of extensibility in mind. And so we have kind of a limited toolkit that we can use to interoperate with the Analyst software. All of the data in Analyst, methods, raw data, process data, are stored in proprietary format data files. And those data files are optimized for performance, not for accessibility. The data and method files don't have any public format. They are accessible only through the Analyst software. So we are completely limited in extracting data from these files to working through the framework that the Analyst software provides for us. So Analyst provides us with a pretty limited toolkit that we can use. There is an API called the Analyst Access Objects, which is intended to allow peripheral device manufacturers to write device drivers for their LC devices, auto samplers, things like that, and to work with the Analyst software. The way that many of those are implemented is as a black box. So the peripheral device manufacturer will define what the parameters for their particular device is. They'll write software, often including a UI, which will hand a block of parameters to the Analyst software. Analyst has no insight at all into the internal structure, and when it interacts with that device, will simply pass that block of information on to the peripheral device. So it's a pretty opaque process from the perspective of someone living in the Analyst universe. We also have an API called the Wiff Reader Sdk. That's a one-way interface that allows us to extract raw chromatographic data from a Wiff file or a raw data file. That is available only through license, and of course we're able to get a license for that for this project. So the instrumentation that we supported, when we began, we wanted to support everything that might occur in the lab. We started with the lofty goal of anything that interoperates with Analyst, we wanted to be able to support in the method adapter. We quickly realized that that wasn't practical, and we scaled that back to only the devices that are in the labs that Henning's working with, and quickly realized that that wasn't realistic. And so we settled on the Sciex blue line of instruments and the Agilent 1100, 1200 series of LCs, also the CTC PAL. We made this decision mainly because these are the devices that the Analyst software really does interact with, rather than just pass on that block of parameters without understanding it. Through the course of development, we ran into a few challenges. We found that the Analyst libraries didn't like to coexist very well with the C# ADF libraries. I'm confident that that would be solvable, But in the interest of time and delivering a proof of concept here, we decided that we just didn't want to worry about that. We didn't want to debug our platform versus the ADF platform in the context of this project. We didn't want to, so we're interfacing with the Labware LIMS, and the back end for Labware is Oracle. We wanted to avoid using the few kind of limited .NET Oracle drivers that were available. We certainly don't want to install the Oracle client on every instrument control workstation where we're going to run this application for reasons of validation and support and so on. And as I mentioned, we decided that the conversion of the instrument parameters from the black box was out of scope. That would require collaboration with other vendors, and we just didn't have time for that. Another roadblock we had, which was problematic, is the lack of a mature data model for the archiving use case. So we see the output of the mass spec working group to be an input for anything we want to do as Sciex, and so that's very important to us as well. So we came up with an architecture to address many of these problems. Over on the left, we have the Analyst software and its proprietary format data files. We created a Sciex adapter application, and that consists of type libraries, a command line interface, and a graphical user interface. We took all of the Oracle interactions and ADF interactions and ported them out to a Java-based web service. So what happens is that a user will have a method in the Analyst environment and decide that they want to transfer that to the repository in LIMS. They'll select that via the GUI or the command line interface. The information from that method is parsed out to the extent that it can be, and the source the acquisition method data file and those parameters are sent to the web service. The web service interacts with the ADF APIs, creates an ADF file, populates the data description and the data package layers, and then writes that to a transfer table in Labware. What this let us do is use the built-in Java Oracle support that was desirable for us, and insulated all of the ADF operations outside of the Analyst.NET environment. So for the analytical method exchange, we extract metadata from the method files, populate that into the data description. We take the original raw format method files and place those in the data package. For the archiving use case, we again extract data, metadata, and place it in the data description layer, and the raw spectrographic data and the process result data get put into the data package. So the use of the transfer table enabled us to have a very clean interface with Labware. So Labware could do whatever they wanted with this data once it was received over there, and we didn't have to worry about the intricacies of the schema behind Labware, how all that should line up. So the acquisition method or quant method converted to ADF, it's placed in the transfer table with some additional metadata. The ADF file is stored as a binary large object in the transfer table, so the whole ADF file is there. When a method is pushed from LIMS back to the Analyst software, an ADF file containing those same data and those source files is pushed back to the Analyst environment. Part of the reason we did this way, rather than try to reconstitute that acquisition method file on the workstation, is that our interfaces to the Analyst software are mostly one way. So we don't have a very clean way to take all of those parameters and put them back into a new method file. So we're carrying the original method file through the whole process. In addition, moving from Labware back to Analyst, we have the capability of including a sample list. So that is the basis for a method, a technique to automate some of this run processing. So in future phases, we may look at the possibility of taking that sample list, the method file, and actually kicking off a run on the instrument. So this is the GUI. Over on the right-hand side, you see the main window for pushing an acquisition method file or quant method file to the LIMS software. We have a query into LIMS where we can see what's already there. Most of this is pretty straightforward. We select a method on the analyst side. We get to see a preview of that. Then we select where we want to send it. It'll be converted to an ADF file no matter what, but we can choose to keep the ADF file for whatever reason or just push it into LIMS and delete the operating system file. Again, we can pull a method out of LIMS so we can query and see everything that's in LIMS, identify where we want that to go, what analyst project we want to put it in, and replace those files on the workstation. For the archive use case, we identify a raw data file and a process data file and a destination for that conversion. And with that, I'll turn it back to Henning. Thank you very much.
Yeah, thank you there for all the details of it. So basically, to sum that up, why we actually wanted to do that. So we wanted to address all these 8 points and starting to integrate coming from a single workstation approach and linking them through a simple method, but just storing methods centrally, avoiding transcription errors throughout the whole transfer process, getting to a higher data integrity and better workflow integration in there. Yeah, making basically having, of course, a central method repository with an easy transfer also from methods from one machine to another, and also having a generic integration, so we're not having only bilateral communications. We expect also that this setup should work for other LIMS and also other maybe also thermal MS files should have the same structure as such. So what are the next steps? So basically, if this was too technical for you, this is the breaking news actually. So we are actually working now on the first non-pharma healthcare use case of allotrope. So we have basically an identical setup, different LIMS, so it's the Abbott Informatics Star LIMS, but most of the identical LIMS in our crop science world, and we are trying to adapt the same adapter in a similar way there. So we're going to carry out this by the end of the year and next year. So there is no argument anymore that allotrope is only relevant for pharma use cases. You just have to look in your labs. Basically, as you've seen, we did not populate so far the data cube because we are still working with the MS Data Cube working group on how to do that and align that. And once this is agreed on, we can target that step. And what we didn't also carry out is basically all the auditor information that's in the Analyst software so far is not transferred to the ADF. So in order to put that into a GMP environment, or GLP environment in that case, we will look into that and maybe leverage also the audit tray capabilities of the ADF. With that, just maybe one outlook, what we think, we've heard that earlier today, that basically if we think of having published methods, published information published in a standard format out in analytical journals, etc., we can in an ADF format we can maybe leverage all that and automatically increase our efficiency in analytical method development cycles. As if you think that your scientists or our scientists are made aware by an AI or machine learning or whatever fancy buzzwords thing you have in mind, that really looks for methods that are relevant to the scientific problem they're about to solve, enriched with publicly the data that is available out there. I think this is what we've done. It's probably the first step going there, harmonizing method data across what's out there and encouraging everybody to store, regardless in which vertical you are in pharma and crop science or in the academia, and making the method development as such more efficient. I think with that, we're done for today, and